Talk today about lesson 20, applications of congruence in terms of rigid motions. So if you have your booklet should be handed out to you, so if not, make sure those get handed out. Make sure that the hander-outer is giving you the right booklet with your name on it. And we want to be on page 114 for today's lesson. Yesterday we talked about rigid motions. Today we're going to talk about how you apply those to compare them between two polygons. So there are really two big ideas here that we're going to discuss. First, we're going to talk about being able to understand that a congruence between figures gives rise to a correspondence between parts. We're going to talk about figures being congruent, but if figures are congruent, that means that there's a correspondence between the parts of the figure. So that corresponding parts are congruent. And hopefully you'll be able to state that the correspondence that arises from a given congruence. And you'll be able to recognize that correspondences may be set up even in cases when there's no congruent present. So I can compare, for example, two sides in a polygon of two different polygons. Compare two sides even though the polygons aren't necessarily congruent. We'll talk about some real-life examples where that matters. And then you're going to know how to describe and notate all of the possible correspondences between two triangles or two quadrilaterals, and know how to state a correspondence between two polygons. So those are the learning targets for today, the overall big picture. And if you follow along on your page 114, we're pretty much going to go through this one chunk at a time. So under the Common Core is the new standards that we're adopting here. Under the Common Core standards, the definition of congruence, we say that one figure is congruent to another. We mean that there's a rigid motion that maps the first onto the second. So let's say we have a triangle here and have another triangle that's located over here. The question is, are these congruent? Well, I can determine that they are congruent based on comparing the shape of the pre-image to the image and saying, is there some way for me to start with triangle ABC and then somehow prove that in fact triangle DEF would be the same as triangle ABC using some kind of transformation. So can I make triangle ABC using some kind of transformation and state that it's pretty much A prime, B prime, C prime using some combination of a transformation? I may have to rotate and translate. I may have to reflect. Any combination of those three things. I can just do one or I can do three of them. So here, if you take triangle ABC, what kind of transformation needs to take place to get to ABC prime? Well, if you think through that for a minute, you realize that with triangle ABC, you're going to have to perform a rotation. And then you're going to have to perform a translation to get them to overlap, so that one maps onto the other. If I could do that somehow, if I could say, all right, let's rotate, and by the way, I'm going 90 degrees, which direction? Positive, right? Positive 90 degrees. Let's rotate it, and then let's apply a vector, and then see if I can end up with ABC prime. So are these two congruent? Well, if I try to overlap them here as I am now, I'm not getting a perfect overlap, so they're not. But if I could, if they overlap perfectly, then I could reach the conclusion that one pre-image using some kind of transformations maps onto the image, which really demonstrates and proves that the two figures are congruent. All right, in grade 7, the definition of congruence was a correspondence between two triangles is a pairing of each vertex of one triangle with one and only one vertex of the other. When reasoning about figures, it's useful to be able to refer to corresponding parts of the figures. So for example, if we take figure triangle ABC here, and we compare, we look at side AB, which side would that correspond to in the other triangle? Well, here it would be A prime, B prime. I could make this slightly more complex. I could take this whole thing. Okay, that's kind of cool. I could take this whole thing and say, all right, let's get rid of these shapes altogether. Not particularly interested in the triangles anymore. And I can make them quadrilaterals and still compare the same shapes to yield the same result. I'll show you what I mean here in a minute. As soon as I get this out of the way. Which probably won't happen. But I'm trying. Okay. Let's do this. Gone. So if I have a quadrilateral, or let's just say like this, parallelogram, and another parallelogram, I could talk about those two somehow corresponding to one another, even if they're not congruent. So these two may not be congruent, but if I use some letters here, A, B, C, D, E, F, G, H, which side would DC correspond to in the other rectangle? I'm assuming it's a rectangle. DC would correspond to HG. So we could talk about corresponding parts even if they're not necessarily congruent. So we might also notice that two triangles look very much alike, and we may match the parts of one with the parts of the other based on the way they look. Or finally, if we know that the two figures are congruent, then they always give rise to a correspondence. What do I mean by that? I mean, if I know that two figures are congruent, which means they have the same, all of their segments are of the same length, and all their angles are of the same measure, then I can automatically say that AB and DEF, those are the corresponding parts, and they're congruent. Since they're congruent, they must correspond. They go with each other. A rigid motion always produces a one-to-one correspondence between the points in the figure, which is the pre-image, and its image. If P is a point in the figure, then the corresponding point in the image is F of P. Let's talk about what that means. Let's pretend that the orange, we'll take for example here, the orange triangle here represents our pre-image. And then the purple triangle represents our image. It'll be this one over here. Now, if I start with A, vertex A, which vertex would A correspond with in the image? Well, if you look closely here, you will see that it's E that corresponds to it. So the question then is, can I take A, which is in the pre-image, and will F of A, which is the rigid motion that I'm going to do, will the rigid motion that I perform on A result in E? That's the question. That is how I would write that. That's how I would have a discussion about it. F here is kind of like a function we have in algebra, but we're using F to talk about, to address the idea. F represents any transformation. It could be a rotation, translation, reflection, or a combination of those. So a rigid motion, back up here, also maps each part of the figure to what we call a corresponding part of the image. So as a result, corresponding parts of congruent figures are congruent, since the very same rigid motion that makes a congruence between the parts, between the figures, also makes a congruence between the parts of the figure. Now you've probably heard people say often in a proof, corresponding angles of congruent triangles, or corresponding sides of congruent triangles. People use those in proofs, but they're really not necessary, because it kind of flows from the definition of congruence. So here's what I mean by that. Looking back at the figures that we drew there, the two triangles that we started with, I have the orange triangle and the purple one. If I can show that ABC and DEF are congruent, those two triangles. By the way, I can. Observe. I'm going to take triangle ABC, I'm going to rotate it 90 degrees, if I can, and then I'm going to place it, translate it, on top of the purple one, and I should get a perfect correspondence. See how they overlap just right? Okay, so taking the orange one back where it goes. The orange one, triangle ABC. If I can show that triangle ABC is congruent to triangle DEF, which we just did, by the way, then all the corresponding parts are necessarily congruent too by definition. So AB, what would AB be congruent to in the image? DE would correspond to it, right? So I can put the little tick marks there to indicate that. How about AC? AC and EF are congruent. How about DF? DF would be congruent to BC. See how they correspond naturally? If the triangles are congruent, then all the parts automatically correspond. That's true for the sides as well as the angles. What does A correspond to? E. They're congruent. What does D correspond to? B. They're congruent. What does C correspond to in the other triangle? That would be F. So all of the angles as well as all the sides correspond. You don't have to say that over and over again. You don't have to use the phrases that are up here. Corresponding angles of a triangle congruent, sides of a triangle congruent. You don't have to use those because it's kind of unnecessary. Okay, there are some correspondences that don't come from congruences. So in the triangles from the previous slide here, we discussed that since these figures are congruent, everything corresponds. But they don't necessarily have to be congruent for me to discuss a correspondence. So on this slide here, you see that there are two figures, two quadrilaterals near the bottom here. So for example, let's say that you are a carpenter. You might want to know if the two windows in an old house are the same, so that the screen for one could be interchanged with the screen for the other. You might list the parts of the first window and the analogous parts, the parts that go with it, of the second. Thus trying to make a correspondence between the parts of the two windows. Checking part by part, he might find that the angles in the frame of one were slightly different from the angles in the frame of the other. Maybe because the house tilted slightly as it aged. He has used a correspondence to help him describe the difference between the windows, not to describe the congruence. So I have two quadrilaterals here. This one would represent the new window. Notice that it's like rectangular in its appearance. And then I have here to the right the other quadrilateral, which doesn't necessarily look like a rectangle. It's shaped slightly, tilted. Let's say the house aged. These old houses, they tend to sink quite a bit. Their foundation is not built very solid. They didn't have the parts that we have today. So he could compare these two figures. He could compare this top side here, this segment at the top, with the segment that's located in the other figure. He can compare those two. He can make a correspondence between them, although they're not necessarily congruent figures. It's possible. So in general, given any two triangles, one can make a table with 2 columns and 3 rows and list the vertices of the first triangle in the first column, the vertices of the second triangle in the second column in a random way. This would create a correspondence, though not generally a useful one. No one would expect a random correspondence to be useful. Later, though, when we study similarity, we'll find that it's very useful to be able to set up correspondence between triangles despite the fact that they're not congruent. Okay, let's have a quick discussion of all of the function notation that we used for rigid motions. And this is important because we've been trying to kind of zone in on this for a while. So a translation, how do you write a translation? To name a translation, remember the symbol that we used? We used a T. T for translate. So the T indicates that I'm using a translation. And what am I translating by? The AB below it there denotes the fact that I'm using a vector to translate. And the letters A and B indicate the translation that moves each point in the direction from A to B in a line parallel to line AB by a distance of AB. So the image of the point, then, is denoted as T of AB, and then notice in parentheses there, I have parentheses P written there. So the P, the T indicates translation, the AB represents the vector I'm going to apply to it to move it around, and then P represents the result. P is what I'm going to apply the vector to. We also talked about a reflection, and we used the symbol lambda, which is an upside down V. And if you remember underneath there, when we name a reflection and we use that symbol lambda, we are writing a little L below it. That little L represents the line of reflection that I'm using. The image of a point, then, P, is denoted as lambda of little l, and I'm applying point P to it. So if A is a point on the line, then lambda L of A would equal A. Because if it's getting reflected, if it was already on the line to start with, it's going to stay on the line of reflection to end with, right? So to name a rotation, we use capital R. So we use a capital R for rotation, and then there are two other parts underneath the R. One is C, which indicates the point around which I'm rotating. The other is X, which represents how far am I rotating. In what direction? Remember, if it's positive, the X value is positive, it means I'm going counterclockwise. I always start over here at my initial side. If I'm going in the positive direction, then I would be going counterclockwise. That's where things are positive. And if my X value were negative, I would be rotating clockwise. That many degrees. Okay. We also, now that we've reviewed all of those, we can apply any of those to a transformation. So here we have a figure below on the left. It's been mapped to the one on the right by a 240-degree rotation around P. You have to identify all 6 pairs of corresponding parts, which are vertices and sides. So what you're going to do with your partner right now is together, you are going to work on filling in the table. So start by filling in the table. And once you fill in the table, you're going to answer the question down below. Both of those are necessary at this moment. So in order to do both of those, I'm going to give you a total of 4 minutes to fill in the table as well as answer the question below. Okay, your time is up, so let's compare and review. First, when I'm looking at the figure here, I need to compare and talk about the corresponding vertices. So of the vertices in the diagram, which would correspond, considering the fact that I know this is a rotation. So if I start with A over here, bottom left corner, I'm rotating around P, so that means it looks like I'm headed in this direction over here. So what does A map onto? A is going to map onto X. So B has to map onto Y, and C has to map onto Z. Now this rotation was actually positive 240 degrees, so when I'm giving you this arrow here, I'm doing that incorrectly. Because it's a positive 240 degree rotation, which way am I rotating? I'm not going clockwise. Positive means counterclockwise. But A still ends up all the way around to X. 240 degrees. B would go to Y, B maps onto Y, and C maps onto Z. How about the corresponding sides? Well, which sides correspond together? Well, AB is going to map onto XY. AC maps onto XZ, and BC maps onto YZ. So that's the corresponding sides and vertices, so write those in there correctly if you didn't quite get that right the first time. What rigid motion maps the triangle ABC onto triangle XYZ? Okay, so we discussed, we were actually given that this was a rotation of 240 degrees. So how am I going to denote that in function notation? Well, rotation means I use which letter? R. What am I rotating around? P. So I'm going to have an R for rotate. What am I rotating around? I'm rotating around P. How much am I rotating? 240 degrees. So I need to write that entire transformation in function notation. So when I do that, I'm going to have to include in parentheses my triangle, ABC. The triangle ABC is what gets mapped onto, what's the result? Triangle XYZ. That's how you'd write that in function notation. Okay, given a triangle with vertices ABC, list all the possible correspondences of the triangle with itself. So draw yourself a triangle in here. Give its vertices. Label them ABC. Let's list all the possible correspondences of the triangle with itself. Well, if I have a transformation of any kind, remember this could be any kind of transformation. It doesn't have to be rotation. I can translate. I can reflect if I need to. What can A map onto? Well, A could map onto A, couldn't it? If I reflected, it would. Especially if I reflected around here, for example. A would map onto A. What else could A map onto? Well, if I rotate, A could map onto B. Or A could map onto C. A really can go anywhere. How about B? B can go anywhere too. It would map onto itself. It was a translation or a reflection, right? Let's say I applied a vector to B going in this direction. Then where would B map onto? Well, B would start over here. It would end over here. B would map onto itself. So B can map onto itself. B can map also onto A. Or B can map onto C if I rotate the whole thing. Same with C. C can map onto itself by a reflection or translation. C can map onto B or A if I rotate. That's an A. Okay, give an example of two quadrilaterals and a correspondence between their vertices. Now this is important because there are two components here. One, the corresponding sides have to be congruent. So corresponding sides are congruent. But corresponding angles are not congruent. So what I'm going to do with your partner here, I'm going to give you some time. See if the two of you can put your heads together. Draw two quadrilaterals, which means four sides, We want corresponding sides to be congruent, but corresponding angles are not. Let's give you 2 minutes, see if you can come up with this with your partner. Go ahead. All right, your time is up. Let's see what you came up with. If you could name the quadrilaterals too, that would be extra bonus points. Really, when you draw the shapes here, you need 2 quadrilaterals, 4-sided, that are congruent, meaning the same length, but not necessarily congruent angles. So sides are congruent, but not angles. How about this first figure? Quadrilateral ABCD, what does it look like to you? Kind of looks like a square. Angles A, B, C, and D appear to be a measure of 90 degrees. How about the one to the right, JKLM? JKLM is a rhombus, which means the sides are congruent, but the angles are not. If you look closely here, you'll see that angle J is acute. What is angle K? Obtuse. So these angles can't be the same. This one is greater than 90. The measure of J is less than 90. All of these appear to be 90. Not saying they are, but they definitely appear to be. So I have a situation here where I have 2 quadrilaterals. I can make a definite correspondence between them. But the sides and angles aren't necessarily both congruent. So the 2 figures aren't congruent. So what would side AB correspond to? Well, angle A would correspond to angle J. Angle B would correspond to K. C corresponds to L, and D corresponds to M. And the sides correspond as well. AB corresponds to JK, all that. With the sides, if AB and JK, which correspond, happen to also be congruent. But with the angles, if I compare angle A in here to angle J in here, what about those 2 angles? They correspond, but they're not congruent. That is the key part of the lesson. Things can correspond and be congruent. Things can correspond and not be congruent. But all figures which are congruent lead to correspondence.